Every algorithm eventually terminates or loops forever, but no single program can predict this behavior for all possible inputs. Alan Turing proved in 1936 that a universal decision procedure for the halting problem is mathematically impossible. We seek an algorithm called H that takes any program P and input I to determine this outcome with total certainty. This hypothetical machine H must always return a result in finite time for every possible pair of program and input. If such a machine existed, we could eliminate all infinite loops in software during the compilation phase before execution. However, the laws of formal logic dictate that such a universal decider can never be constructed in any computational system.
To prove this, we first established that all programs can be represented as discrete data strings or unique binary integers. A Turing machine consists of a finite state controller and an infinite tape divided into cells for reading and writing symbols. Every Turing machine can be encoded into a binary description, allowing one machine to process the logic of another machine. We define the halting function as a mapping from the set of program and input pairs to the binary set. In our model, 1 represents the termination of the program, while 0 represents the occurrence of an infinite loop.
Assume for the sake of contradiction that a total computable function h exists to solve this halting mapping for everyone. Function h takes two specific arguments, the source code of program P and the input data string labeled as I. If program P halts on input I, function h returns true. If program P loops forever, function h returns false. We now construct a new specialized program called D, which stands for the diagonalizer, to challenge the decider H. Program D takes a single input, which is the binary source code of any arbitrary program labeled as P. Inside its logic, program D immediately calls our hypothetical halting decider H to analyze the provided input code. D passes the source code of program P to function H as both the program to check and the input. Program D then evaluates the specific binary result returned by function H to decide its own subsequent computational move. If function H reports that program P halts on input P, then program D intentionally enters an infinite loop. If function H reports that program P loops on input P, then program D terminates its execution immediately. This internal design ensures that program D always does the exact opposite of what function H predicts for program P. Now we encounter the logical crisis. What happens when we run program D and give it its own source code? This means we are evaluating the behavior of program D when applied directly to the technical description of itself. We pass the string representing program D into the internal function H as both the program and the target input. Suppose function H predicts that program D will eventually halt when given its own code as the primary input. Based on our definition, if function H returns true, program D must follow its internal logic and loop forever. This results in a direct contradiction. The decider predicted halting, but the program actually executed an infinite loop. Now consider the alternative. Suppose function H predicts that program D will loop forever when processing its own code. In this case, function H returns false, which triggers program D to terminate its execution and stop immediately. Again, we reach a contradiction. The decider predicted a loop, but the program halted. H is wrong once more. Since H cannot be right regardless of its output, the initial assumption that function H exists must be false. This proof by contradiction demonstrates that the halting problem is undecidable in every standard model of general computation. The result is not a failure of current technology, but a fundamental and inescapable boundary of mathematical logic. It implies that there are specific, well-defined questions about program behavior that no computer can ever answer. This undecidability extends to almost all non-trivial semantic properties of programs, a result known as Rice's theorem. We cannot write a general program to check if code is free of viruses, or if it always halts. The halting problem also links computation to the busy beaver function, which grows faster than any computable sequence. It proves that there is no algorithm to determine if an arbitrary set of Diophantine equations has an integer solution. Gregory Chaitin expanded this into the study of algorithmic information theory and the definition of the number omega. Omega represents the exact probability that a randomly constructed program will eventually halt on a universal Turing machine.
This number is not only uncomputable, but also contains infinite information that is logically irreducible and truly random. Turing's discovery ended David Hilbert's dream of a mechanical procedure to solve every possible mathematical problem in existence. The Entscheidungs problem was settled negatively, proving that human and machine reason have inherent formal limits. Computation is a landscape filled with unanswerable questions, forming the undecidable core of our modern digital world.